Okay, let's recap isomers one more time. We said we have defined previously isomers are those units that have the same molecular formula, and they have different structural formula. Structural formula. And it is by virtue of these differences in the structural formula which lead to various different kinds of isomerism, which we are going to talk about throughout the course. Here, I want you to bring from your memory, recall the concept of constitutional isomers. There were other words for these, such as isomerism, skeletal isomerism. So a classic example would be that is shown here, where I have butane, which means it is a C4, 4-carbon containing unit, and isomer of butane, that would be isobutane. So notice the difference in here. You have 4 carbon atoms, 1, 2, 3, and 4, and all I'm doing is I have brought in the 4th carbon as a pendant to the main 3-carbon necklace. So envision that in one case you have no pendants, it's just a string of 4 carbons. In the second case, you have 3 in a row, and then coming off of the second one, you have a little methyl group. Okay, so that's the basic difference between the two. So another way to view this would be, in one case you have the 4th carbon tugging out of your 3rd carbon center. In the other case, you have the 4th carbon coming out of your 2nd carbon center. So two different views to see the same thing, but long story short, you see the differences in the structural formula, but the molecular formula for both of those would be C4H10. Okay. Another one that this would manifest as would be a functional isomer. So a functional isomer, as we have talked about previously, functional groups render chemical properties or physical properties of a specific kind, depending on which functionality we are talking about. So for instance, I'm showing you here ethanol. Ethanol means you have 2 carbon atoms, so that's why we are calling ethanol. Your OH is coming off of the first carbon, and we are comparing it to dimethyl ether, which is CH3OCH3. So just by the look of it, if I were to ask you ethanol, 2 carbon unit, OH coming off of it, we talked about that in class as well. You have a functionality which is the alcohol, and the moment you see an OH in your mind, what is that one phrase that should come to your mind? Yep, hydrogen bonding it is. And hydrogen bonding means what? That is correct. You are thinking about, if you're thinking about boiling point and melting points to be high, that is what I was seeking. So if you have a high boiling point and melting point for the alcohol, because of the presence of hydrogen bond, and in case of dimethyl ether, that is not the case, because your hydrogens are connected to carbon atom, and that's not electronegative. So recall, the requirement for hydrogen bonding is hydrogen directly connected to FON, F-O-N, fluorine, oxygen, nitrogen. And so functionality or functional isomerism is another way how constitutional isomers could manifest potentially. Basic idea being that the OH is coming off of your first carbon atom. So oxygen is kind of at the terminus. This is the terminus. It is not in the middle. So it's not sandwiched in between the 2 carbon atoms. So that's another way that you could see this. A third way that you could see this would be the case of propylamine and isopropylamine. And again, it's a functionality. You have 3 carbon units here, with the NH2 being at the terminus at the end. On the other hand, in the first case over here, I have the NH2 coming off of the 2nd carbon atom. So again, the position of the group is changing. Sometimes this is also called as the positional isomer. Okay. Okay, let's talk about the condensed forms and the extended forms one more time. We've talked about the line angle skeletal, so hopefully everybody has gotten comfortable with that. But this slide essentially shows you what we have discussed previously too. If you have butane, we are looking at a C4 chain. You could look at the butane as 1, 2, 3, 4 carbon unit completely extended out. However, each of the CH2s has been consolidated, so you would classify this as the condensed way of writing. You could also condense the CH2s further as a CH2 whole twice, and that's indicated the second and the third carbon are incorporated within the chain. So this terminus methyl group is exactly what you see on top. This methyl group over here is going to be your CH3 that you began with. If you wanted to write down the complete extension, that would be your Lewis structure over here. Each of the hydrogen and carbon bonds have been shown. But of course, we are a big fan of which kind? Line angle skeletal. We talked about that back in chapter 1. So you want to continue to write those, and this is what I would seek in the nomenclature questions come exam 2. So get used to that ASAP, but I just wanted to kind of throw it out there that what you learned from chapter 1, how to write down the Lewis structures, how to derive the condensed structures, that's not going anywhere. It still holds true. You could write it for any organic compound for that matter if you wished to. All right, so one thing that I would want to remind you, the concept of alkyl group. An alkyl means that out of the alkane, you have removed just one hydrogen, and what remains is alkyl. So methane, for example, will give you methyl, ethane will give you ethyl, propyl, butyl, penyl, hexyl, heptyl, octyl, nonyl, decyl, as we go. So again, just to make sure everybody is on board, if I were to write down, let's say methyl alcohol, all right, methyl alcohol, and of course we call it methanol. That means it's being derived from the methane. So that's my methane, 4 hydrogen 1 carbon unit. Now I'm going to take away, so I'm going to take away one of the hydrogens, and I'm going to replace it with the functionality. It's an alcohol, right? So what should I bring in? That's right, OH. So I'm going to replace the H by OH. So the structure becomes CH3 OH. And so your CH3 part conforms to the methyl, the OH part conforms to the alcohol. So methyl means that you have a CH3. So still the same idea, but I wanted to kind of just remind you of that. Let's also, while we are at it, talk about the primary, secondary, tertiary, quaternary carbons, and consequently primary, secondary, tertiary hydrogens. What are they? So if in your chain, your carbon is connected to just one other carbon atom, you're going to call it a primary carbon atom. If it's connected to 2, we are going to call it a secondary. Connected to 3, we call it a tertiary. Connected to 4, we call it a quaternary. So if you have maybe, let's say you have butane, okay? Now, if you consider, I'm just going to number these. Numbering goes a long way. So if you had position 1 and position 4, those have only one neighbor right over here and here. So that means position 1 and 4 should be deemed as a primary carbon atom. On the other hand, if you look at your position 2 and 3, they have two neighbors. Carbon 1 is a neighbor, carbon 3 is a neighbor for C2. Likewise, for C3, carbon 2 is a neighbor, carbon 4 is a neighbor. So those two should be called as your secondary carbon atoms. If you had, on the other hand, if you wanted to compare that to perhaps isobutane, so now I have 1, 2, 3, and 4. So if I have to locate all of my primary carbon atoms, I would say that carbon 1 has only one neighbor, C2. Carbon 3 has only one neighbor, C2 again. Carbon 4 has only one neighbor, C2 again. So there are 3 primary carbons. We write that as 1 degree. And carbon number 2 has actually 3 neighbors. So we are going to call that a tertiary carbon atom. And likewise, if you were to look at a carbon center which has all neighbors which are carbon atoms, we are going to call that particular carbon a quaternary center. Turns out that the hydrogens that are present on a primary carbon atom are called primary hydrogens. So for example, going back to the example of butane, I had 3 in the methyl, right? So all of those are going to be called as the primary hydrogens. Likewise, the hydrogens that are connected to a secondary carbon are called as the secondary hydrogens, and the carbons that are connected to a tertiary carbon are called as a tertiary hydrogens. No points for guessing. There is nothing like a quaternary hydrogen because guess what? Recall, the carbon is connected to 4 carbon units. There is no hydrogen because remember, carbon is not pentavalent. All right, let's go forward. Okay, so over here I am showing you a molecule. So let's draw that out. Of course, here I have drawn it in a condensed structure, and you can hopefully see that I have my primary hydrogens on the methyl groups. The one over here in blue is a secondary hydrogen. It's on a methylene, as we call it. So CH3s are methyl. CH2 is a methylene, and the CH is a methine. It's a little bit of a jargon there. So a tertiary position, also called as methine. CH2, again, a methylene, and CH3s will be the methyl group. Let's do another one while we are at it. So maybe I'm going to just decorate it a little bit and ask you, maybe I'll put a ring just for fun, and a methyl group, okay? And I ask you how many of the primary, the secondary, the tertiary, and the quaternary. Always a good idea to just number them so we can just locate it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And so if I had to locate where my primary carbon atoms are, recall all the terminal methyl groups. They are your primary centers. So position 1, 2, 3, and 12. So 1, 2, 3, and 12. There are 4 of those. Total number comes out to be 4. If you locate the C4, that is connected to all carbon atoms on each side, I'm going to call it a quaternary center. So we found only one of the quaternary. C5, C7, C8, C9, and C11. All of those are CH2s. That means they contain 2 neighbors each. That means total number of methylenes is going to be 5. And then if you look at C6, I'm going to maybe put a triangle on that. And then C10, they have 3 neighbors. So those are going to be my methine or tertiary carbon atoms. All right. So quick recap, methane gives you the methyl, ethane gives you the ethyl, propane gives you the propyl, butane gives you the butyl, pentane gives you the pentyl. I also want to emphasize on the acronym that we have here. Methane becomes methyl. So notice that we have taken advantage of just the first 2 letters. Ethane becomes ethyl, ET. Propane becomes propyl. Butane becomes BU. And pentyl is also called as amyl. Those don't have an acronym, but the first 4 will hold true. Likewise, if you had a benzene ring, which you will, those of you who have to take organic too. So if you have a benzene ring, that will be a pH. Okay? All right. let's talk a little bit about the word iso. So I told you butane is the normal butane, that is the N-butane, but the isomer of that is isobutane. So if you had a 4-carbon chain, just explained that to you a couple minutes ago, quick recap. Iso would mean that the fourth position, the fourth carbon, that methyl group, is hanging off of the second position, not the third position. Okay, so you could have isopentane, isohexane, etc. by having a methyl branch on the second. So the next to last carbon basically means the second carbon. It's not the peripheral, but the second one. So isopentane would automatically mean that the total number of carbon atoms should be 5, and the methyl is going to hang off the second position. Likewise, if you have isohexane, your main chain is going to contain 5, and the second position will have your 6th carbon as the methyl group. Now, as the isomers, as organic chemistry grew and more derivatives were, more and more compounds were discovered, they came up with neopentane, for example, which was a 5-carbon chain, and in that it's the most highly branched structure, which does contain a quaternary center too. So notice what I just said. I said that it's highly branched, high level of substitution, and you have a quaternary center. So another way to view things would be that the higher the level of between primary, secondary, tertiary, quaternary, quaternary is the highest substituted, followed by tertiary, followed by secondary, followed by primary. And also know that as you are increasing, one good practice would be, as you're increasing the number of carbon atoms, take a moment to draw out the possible structures and perhaps identify the primary, secondary, tertiary, that will open up your hand in terms of what are the possibilities, and if you can identify and view what's primary, what's secondary, which one is methylene, which one is methine, and perhaps even try to name them. The initial names were, of course, the CA names. They are your usual butane, N-butane, isobutane type of names. But as chemistry grew, there were more issues because more and more compounds were being discovered, and we did not really have a system to name them. So we are going to learn how to name these organic compounds next. So let's take a quick look at the N-pentane. The N again stands for, yes, you got it, normal pentane. C5H12, I have written C5H12 for isopentane. I have written C5H12 for neo. That makes the 3 of those what? Yes, it's isomers. So notice I have my 5 carbon atoms, right? And I have my 4 in the main chain, and then 1 is hanging off. And then in case of neopentane, I have 3 in the main chain, and then 2 are hanging off. So the basic difference between the 3 is the level of substitution. And if I were to provide the name, the IUPAC name, which stands for the International Union of Pure and Applied Chemistry, and that is the body that comes up with the rules as to what is the systematic name. So another name would be systematic name, IUPAC or systematic name. So if you look at isopentane, the rule says that we have to look for the longest continuous chain. The longest chain in this looks like the 4-carbon unit, right? Because if you went from 1, 2 to 3, that would, like if you were to go this way, that would be not considered the longest chain, because that will contain only 3 carbon atoms. So the longest is the straight chain containing 4. So I'm going to call it a butane. And it's the kind of butane, the second carbon of which is holding a methyl group. So I'm going to call it 2-methyl butane. Now, you might say, what would happen if this methyl group were to hang off of the third carbon? Well, we will just start numbering in the opposite direction, because really there is no need for us to always number from the left hand side, right? These are three-dimensional molecules, and so they are equivalent in all possible directions. It doesn't matter whether you go left to right or right to left. The rule says you have to give it the lowest possible number to each of the substituents. And so rule number 1, again, you are looking for the longest possible chain. Rule number 2, you're giving the lowest possible numbers to all possible substituents. All right, let's take a look at the third one to see if we are able to put it together. We have a propane, because it is a 3-carbon chain. If you really didn't want to go horizontal and just for the sake of argument, you wanted to go kind of vertical, I'm going to do that too. It really is a 3-carbon chain, so I'm going to call it a propane. At position 2, you have a methyl, and position 2, you have a methyl. So you're not going to call it 2-methyl. You're just going to call it 2,2-dimethyl. So you're going to consolidate and use the Greek prefix di-tri-tetra in order to emphasize on the number of such groups. We typically don't use mono. It's a little redundant to say, hey, I have only one of them, right? Because that would mean that you are just writing it once. So we're just going to call it 2,2-dimethyl propane. Notice the use of the comma in between the two numbers. Notice the use of the dash between numeric to alphanumeric. So keep that in mind when you go between the numbers. You have to put a comma in between the number and the letter. You're going to put a dash. Good. Can we go forward? Good. Okay, so let's quickly just talk about the rules. I told you the first rule is you will be looking for the longest continuous carbon chain. That's step number 1. You will number the carbons. So you're not going to just always pick left to right. You could go right to left, top to bottom, make a C shape, make a Z shape, make an L shape, whatever it is. It doesn't matter. You have to get the lowest possible numbers. So you have to number it in a manner such that it's closest to the first branch. You would then name the groups that are attached to the chain. So whether it's ethyl, methyl, what kind of substituents, that's what we call the substituent. Some people call it substituent, some people call it substituent. There is that difference between British English and US English. You have to alphabetize them. So ethyl, for example, will come prior to methyl. You do not use di, tri, tetra to alphabetize, okay? The use of di, tri, tetra tells you solely how many of those groups are present. So you use that to consolidate, just the way we saw previously. Okay, so over here, let's try to just put it together and see if we can identify. So if you look at 1, 2, 3, 4, 5, 6, 7, that's a possibility. You could also go 1, 2, 3, 4, and then 5, 6, and 7. Notice that you could have gone in the other direction. So you could have said 1, 2, 3, 4, 5, 6, 7, but that would give higher numbers to the methyl and the rest of the substituents. So not probably the best idea. And so the next rule is that when you are numbering, you want to incorporate as many substituents on your chain that you have chosen as possible. So I would go, let me use the eraser to get rid of things that I don't need. I would go with what's remaining, the one that's highlighted. And that would be my main chain. And since it's a 7-carbon chain, I'm going to call it a heptane. It's the kind of heptane, the third position of which has a methyl and another methyl, and the fifth position has a third methyl. There's 3 methyls. So you would call it a 3,3,5 dash trimethyl, right? And the other group is a 1 carbon, 2 carbon, 3 carbon. 3 carbon unit is called a what? Propyl. So in the battle of alphabetization, what would win? M or P? M. So that should be the one that you put first. So the name will become 3,3,5 trimethyl dash 4 dash propyl heptane. The full name is 3,3,5 trimethyl 4 propyl heptane. All right, let's see if we can work on another one, and we'll learn about a rule as we go. So over here, I'm showing you another molecule, and I've numbered it the way I have, but I also want to present another possibility. 1, 2, 3, 4, 5, 6, and 7. Notice that I could have used, if I wanted to, this methyl group right at the bottom and the top. So I could have gone either way, either one here or one there. So either of those are possible. They're equivalent. But which one would you rather prefer, the red or the blue? In this particular case, yes, it should be the red. And the reason for that is what? Because if you consider, you basically have the same number for the two methyl groups. So why the difference? That's right. It's the ethyl group which is going to receive lowest number in going from left to right. So 7 carbons makes it a heptane. Position 2 and position 6 contain the methyl group. So I'm going to call it 2,6 dimethyl. And then third position has an ethyl. So in, again, the battle of alphabetization, you have ethyl that's going to take over because it's an E versus the M for the methyl. The whole name becomes 3-ethyl-2,6-dimethyl heptane. Good? All right. So let's talk about again the simple substituents and the complex substituents. So again, CH3, 1 carbon unit is a methyl, 2 carbon unit is an ethyl, propyl for 3 carbons, butyl for 4 carbons, and we have some that are also referred to as the complex substituents. Complex substituents. So if you have a 3 carbon unit and the point of attachment is, let's say this is a long chain, okay, and you have 3 carbons. I'm going to call 1, 2, 3. You have 3 carbons and the point of attachment is right over here. You call it a propyl chain, right? You call it a propyl chain because there is your 3 carbon atoms. If you have, instead of a straight chain, I'm going to kind of make a parallel. And let's say the point of attachment was not the first, but the second carbon. What do you think would the name be? Since it's an isomer, right? It's not the propyl on its own. It's an isomer of the propyl. We call it the isopropyl. Remember what iso was? Iso was when the methyl hangs off the second position. Here the methyl is hanging off the second position. That's why iso. I remember when I was a student, I used to always look for these patterns, these takeaways that would help me remember things. So one pattern that I went with was I is Y. That means when I need an isopropyl or iso whatever, I should be seeking this Y-like shape. And so that helps me remember when there are complex substituents that get complicated. For instance, let's take a look at isobutyl. So isobutyl means I'm looking for a Y-like shape. Does that look like a Y? Absolutely. So your point of attachment is right over here. You have total 4 carbons, but notice this is not, this is not the direct attachment here. It's an attachment. The methyl group is coming off of the second position. So that's isobutyl. Sec-butyl would be if the secondary, so you have a butyl chain, but it's the secondary position, which is the point of attachment. So another way to draw that would be this. And then sometimes you would also find this spider doing yoga, or maybe a mosquito. I don't know. 4 carbons at was what it looks like. It looks like a tree to some people. Basically, it's the tertiary location, which is the point of attachment. So whether you want to call it tertiary, and remember the T for tertiary, absolutely fine to do that. And notice that, make a note somewhere that the tert and the sec would not be counted in the nomenclature. So it's the B that you count. Whereas when you have isobutyl or isopropyl, it's the I that will be counted in the alphabetization. Okay? All right, so just to again reiterate, give you another way of seeing things, I have a N-propyl. The point of attachment is through the terminal position, and so that's why we are calling it an N-propyl. On the other hand, if it was isopropyl, the point of attachment will be from the secondary position. If you do the same thing for the N-butyl, the point of attachment is through the primary carbon atom. On the other hand, if the point of attachment was from a secondary position, we are going to call it a sec-butyl. And if we were to compare the isobutane, so if the point of attachment was through the primary position, we will call it an isobutyl. If the point of attachment was through the tertiary location, we will call it the tertiary butyl group. Okay. I think we have already solved this one. All right, so let's write down some structures. Let's apply this. So you are given 3-ethyl 3-methyl pentane. Pentane means you have a 5 carbon. Always a good idea to first provide the structure of the root name, family name, mother name, however you want to call it. At the third position, you want an ethyl. At the third position, you also want a methyl, and you're done. Now, sometimes I get a question, Professor, can I draw it one methyl on top and the other methyl at the bottom? Absolutely. As long as this looks like a tetrahedral, you're good to go. All right, let's take a look at 4-T-butyl 2-methylheptane. Those are 7 carbons for the root name. 1, 2, 3, 4, 5, 6, and 7. Fourth position has a T-butyl group. Second position has a methyl group. We're good to go. The next one is a 5-isopropyl 3,3,4 trimethyl octane. Octane means C8. 1, 2, 3, 4, 5, 6, 7, and 8. Fifth position has an isopropyl. Third position, and fourth position have methyl groups. So we are good to go here too. Heptane is again C7. 3, 4, 5, 6, and 7. Third position has an ethyl group. Second position, fourth position, and fifth position have a methyl group. And we're done. Notice a couple things. I numbered these just so that I don't make a mistake in a test. If you don't have the correct number of carbon atoms, you do not get any credit. And after I drew the root name, which is the first thing you should do because that itself contains 50% of the points, and then I took the time to put in the substituents. So make sure you follow that. All right, let's see if we can do the reverse. So I'm giving you the structures here, and we would find out the names. So a couple things. Which direction would you start? So if you go from left to right, you're going to get 5 for the isopropyl. Notice these two are going to be 3 and 6. Another possibility, let's do that in blue. 1, 2, 3, 4, 5, 6, 7, and 8. You got that right. You should go in this direction because that will give the fifth position a lower number. And so this is an octane. So it is an octane, and it's the kind of octane, the third position and the sixth position of which has a 3,6-dimethyl, and the fourth position has a isopropyl. So it becomes 4-isopropyl 3,6-dimethyl octane. Let's work on the second one. Or before we go to the second one, I'm not so sure if you analyzed perhaps, going in 1, 2, 3, 4, and then upwards. That would only be 1, 2, 3, 4, 5, and 6. So that has less number of carbon atoms. So not the most appropriate choice. Just wanted to throw out there so that you evaluate and get into a habit of evaluating every single carbon atom. All right, let's go move over to next molecule. You have over here 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Notice I'm numbering in the direction where I'm finding most of the substituents. You probably would not have used 1, 2, 3, 4. That would be less number of carbon atoms. So decane is what I'm seeking here. That's decane is what I have found. Position 2 and 6 contain dimethyl. Position 5 contains, what kind of group is that? It's not iso. It is the sec-butyl, absolutely. And fourth has the ethyl. So 4-ethyl. And I have fifth position, which has sec-butyl. Are you wondering why the sec-butyl was placed first? If you are, well, recall that the S doesn't count, the B counts, right? So it's a competition between the B for butyl, E for ethyl, and M for methyl. That's what you're comparing. Absolutely. All right, let's go forward, and I want to give you like 10 seconds to come up with a name, and then I'll tell you how you were supposed to provide the numbering and what works for the third one. Okay, so if you chose this numbering system, well, the maximum number is 6, but that is not going to be the accurate one. What I want you to do is start here. 1, 2, 3, 4, 5, and 6. Because in doing so, at position 2, there are 2 methyl groups. And at position 3, there is an ethyl group. So total number of substituents will be 3. On the other hand, if you would have gone left to right, the total number of substituents would have been just this t-butyl group, right? So it will be hexane. It's a kind of hexane, the second position of which contains 2 methyl groups. So I'm going to call it 2,2-dimethyl. And then the third position contains an ethyl group. So the name becomes 3-ethyl 2,2-dimethyl hexane. Notice for 4, you must number in this direction. So that's a hexane. Position 2, 3, 5 contain the trimethyl groups, and the name becomes 2,3,5-trimethyl hexane. All right, let's take a look at 5. Hopefully by this time you've gotten a hang of it. We have 7 carbon atoms, so we have a hexane. The second and the fourth position of which have dimethyls, and fourth position contains an ethyl. So the name becomes 4-ethyl 2,4-dimethyl hexane. Likewise, if you look at the last one, you could go 3, 4, 5, 6, 7, 8, 9. One might argue that you may be able to go 1, 2, 3, 4, but recall again, you want to include as many substituents as possible. And if you go the blue route, like the C, you would have one substituent here and another substituent here. So those are the 2 that you would want to pick. So this is a kind of nonane, which is 4-methyl 5-butyl, right? And then you would want to alphabetize it. So 5-butyl is going to come prior. So the full name will become 5-butyl, 4-methyl nonane. Alrighty. Let's see how this might look in a multiple choice format. I have for you some names. All of them are heptane, so you can't just eliminate. You have to look for the longest chain. I'm looking from, you will have to go up to locate your heptane, 5 and 6. So it's not straight chain. It is going to go in this direction. You may have thought of 3, 4, but notice that will give higher numbers, so that's a bad idea. So we would want to use not the blue, but rather the red method. And let's put down the numbers. So we have the methyls. There are 2 methyls. And what kind of group is that? That is a T-butyl. So putting it together for ourselves, at position 3, we have 2 methyl groups, so that's a 3,3-dimethyl. At position 4, we have a T-butyl group, not an isobutyl group. So those 2 choices are automatically out of the window. And then don't forget that you have to alphabetize it, right? So the tert, does that count? No, it does not count. You will be counting the B for the butyl. So 4-T-butyl, 3,3-dimethyl heptane, number 3 is the appropriate answer. All right, let's talk about the nomenclature for when your substituent is a complex substituent. How do we do that? So basically, let's go back and pick one of the molecules from what we have seen in the past. Perhaps I can pick the one that had 1, 2, 3, 4, 5, 6, 7, 8, and 9. And I think there was position 2, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And the 5th one had sec-butyl group, right? This is the molecule. So when you're going to locate your name, the mother name, that still is going to be nonane. Position 2 has a methyl. Position 6 has a methyl. So this is a 2,6-dimethyl system, right? We know that. Now, this was 5-sec-butyl. But what we are going to do is we are going to change the name of this 5-sec-butyl because that's the complex substituent. So how else can we name that? Step number 1. We are going to look at the point of attachment, and the carbon that is the point of attachment becomes 1'. And now I'm going to locate the longest chain again. So 1', 2', 3'. If you find 3 continuously, you would say that this is some kind of a propyl chain. It is a kind of propyl chain, the first position of which has a methyl group. So this becomes 1-methyl-propyl. So one way to say that is that sec-butyl is also called 1-methyl-propyl. And the need for this again goes back to we had started finding out molecules which no longer just had the isobutyl, the isopropyl, and the T-butyl and the sec-butyl. There's more. So rather than complicate things, we just said, you know what, IUPAC really works. So why don't we come up with a system that can give the name to those complex substituents as well. So the only thing you got to remember is that this entire 1-methyl-propyl will need to be in parentheses. So when you have to put that together, you would say that, well, at position 5, so at position 5 over here, I have a chain, and that chain has a chain within the chain. So we are saying that we have some kind of a necklace. We have a pendant out of it, and within that pendant, we have some little substituent as well. Okay, so if I were to signify the main chain, this will be the C9. This chain is going to be the propyl chain, C3, and this chain is going to be the methyl coming out of it. Okay, just to give you an analogy of that. Now, how do we put it together? So you have position 5 with 1-methyl-propyl, and you have 2,6-dimethyl. So you have a methyl group to compare against the methyl-propyl. So since you have the propyl following methyl, there is something that continuously is still continuing. you would give priority to the methyl alone, and that will be named first. So you would call it 2,6 dimethyl 5 parentheses open 1-methyl propyl parentheses close nonane. It's the difference of when you say Sharma and you have Sharma, right? The first 6 letters are going to cancel the first 6 over here, but something else still follows. So you want to keep that in mind, that whenever you have the methyl propyl, the methyl and methyl will cancel, but then something else follows in the methyl propyl. So that should be the one that is going to be named later. The one sort of rule to be broken from what you have seen previously, we never counted the di, tri, tetra previously, right? But if it is a part of the complex substituent, then you gotta name it. So for example, if you had a T-butyl group, and that will be named how? So let's say that's the point of attachment. This is 1 prime, and you do what? You find out, you determine the longest chain. So this is some kind of an ethyl. It's the kind of ethyl that has 2 methyl groups. Where? At position 1. So the name becomes 1,1-dimethyl ethyl. So this D in the dimethyl ethyl will count. Yep. All right, let's see if we can put this together. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8, and 9. 9 means what? Nonane. Position 2 and position 4 have what? Methyl groups. Position 5 has what? That's a point of attachment. 1 prime, 2 prime, 3 prime. So we'll call it a 2,4 dimethyl. Position 5 has 2-methyl propyl nonane. Sound good? Let's take a look at B. 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so that's a decane. Position 2 and 3 have dimethyl. That's the point of attachment at 6. What goes in the parentheses? 1 prime, 2 prime, 3 prime. So 2-methyl propyl again. So hopefully you're seeing that isobutyl is also called 2-methyl propyl. 1-methyl propyl was sec-butyl. Sec-butyl was 1-methyl propyl. 1-methyl propyl. And T-butyl was 1,1-dimethyl ethyl. Yep. And isopropyl, that is 1-methyl ethyl, only one. All right, let's take a look at another one. 3, 4, 5, 6, 7, 8, and 9. So that's a nonane. It's the nonane with second position having a methyl. And what do we have at 5? We have 1 prime, 2 prime, 3 prime. So 1, 2 dimethyl propyl. What should I do? Yes, I need to change my alphabetization. So I must start my name with the 5, 1, 2 dimethyl, because there is a di within the name, and then say 2-methyl nonane. Okay, let's take a look at the last one. So if you would go 1, 2, 3, 4, 5, 6, 7, 8. If you go 1, 2, 3, 4, 5, 6, 7, 8. And if you go 1, 2, 3, 4, 5, 6, 7, 8, 9. Looks like that's the longest. And if you could go 1, 2, 3, 4, 5, 6, 7, 8, 9. So it sounds like the 5th position contains the branching. So it's a nonane again. 5th position contains that. So that's where the parentheses is. That's the point of attachment, 1 prime, 2 prime, 3 prime. So it's some kind of a propyl chain. Is a kind of propyl. The first position, second position have a trimethyl propyl. So 5-122 trimethyl propyl nonane. All right. Okay, draw the structures and give their more common names. So 1-methylethyl. I just find it easy to draw from the point of attachment. So that's my 1 prime. I want to go for the root name first. So that's an ethyl. Is the kind of ethyl, the first position of which holds a methyl. So 1-methylethyl is this. Anybody wanna give a name to this Y shape containing 3 carbon atoms? You got it, it's isopropyl. All right, let's take a look at the 2-methylpropyl. And you know what? I'm gonna give you 5 seconds to work it out because it should take you no more than that. So we got this again, it looks like a Y shape, but it contains 4 atoms total. So what should be the name? I means Y, so isobutyl. Likewise, if you go for the 1-methylpropyl, that means at point of attachment, go for the 3 carbon atoms. First position is a methyl, and so that becomes a sec-butyl. And the 1,1-dimethyl ethyl is going to be your T-butyl. All right. The question states draw the structures of. So let's go for it. You can pause me at this point of time and work it out. That is the best way to learn, and then just match up. So that's your heptane. Fourth position has 1-methyl ethyl. So you have 2 carbons, 1 prime, 2 prime, and the first position has a methyl. You could have called it 4-isopropyl heptane too, but that's the complete IUPAC name. So in your test too, yes, absolutely, I would ask you, whenever I ask you nomenclature, there could be some that are just CA names, some that will say nothing can be more clearer than provide the complete IUPAC name, including the IUPAC for the complex substituent. I mean, what could be more clearer than that? So then I would expect you to know, and then you would have to call this not 4-isopropyl heptane, but rather 4,1-methyl ethyl within parentheses and then heptane. All right. Nonane, how many carbons? Did I get it right? I mean, other than the bond angle. Okay. 1, 2, 3, 4, 5, 6, 7, 8, and 9. And at position 5, you have what? You have propyl. 1, 2, 2. Good. All right. This is an assignment for you. 9 isomers of heptane. Draw all the possibilities. Look for the primary, secondary, tertiary. Look for the complete IUPAC name. See if you can get the complex substituents and go with that. And that is a great, fantastic practice to practice. Remember, I said on day 1, 3 ways to learn organic chemistry. And the last stage of that to finesse yourself is to come up with a question and determine the answer. And absolutely, you can send me a remind message to take a look at it. All right, so I'll leave that for you to work on.